If I know the scores for one variable, I know the scores of the other variable. It's a perfect predictor. If I know x, I know y. Okay? So now, if you're talking about it with z-scores, it's very simple. Because if you have perfect correlation, then your prediction rule would be very simply z, you see that subscript y prime? That's what it's called, that little line. It's called prime. So y prime. And y prime means the predicted y, the y you would predict. So if you're talking about this in z-scores, then z of y prime equals z of x. The z-scores are the same, right? That's what we said in correlation. If you have a perfect relationship, the z-scores are the same. The locations in the distributions are the same. Or if it was a negative correlation, so it would be like that. Okay? But again, this is only if you have a perfect correlation. It never happens, or rarely happens in the social sciences. So what's our modified rule, our modified prediction rule? Our modified prediction rule looks something like this. Okay? Z of y prime equals r times z of x, the correlation coefficient. Move it down. Huh. Yeah?
Why is it y prime and not just y?
Because y is your score. Y prime is your predicted score.
Okay.
Okay? Remember, that's what we're trying to do. We're trying to predict y from x. You could try to predict x from y, in which case you just have to switch everything around. But all the examples we're going to be doing is predicting y from x. So y prime is your predicted y. Okay? So my modified rule is z of y prime equals r times z of x. I'm modifying this rule by the strength of the relationship. Right? So if my correlation is perfect, that would be, let's say, 1, then z of y prime is going to be z of x. Right? That's what we said before. But if it's not, it changes this a little. Now, if your correlation is 0, there is no relationship, then let's take a look at what that is, because that's an important little concept. Let me draw a graph. Okay, so here we have our points are all scattered kind of circularly, right? That's a picture of what kind of correlation? 0, right? There's no relationship. And again, think of what the picture looks like. What it's saying is, as x is increasing, we know nothing about y. Some of the points decrease, some of them increase. There's no relationship. There's no systematic relationship between what x is doing and what y is doing. So the correlation here is 0. Okay? If I was going to put a line through this would be the line. That would be the line. That line happens to fall out at the mean of the y-scores. So here's kind of the concept behind this. In the absence of correlation, right, in the absence of a relationship between x and y, if you want to predict y-scores, what's your best guess? What's your best predictor for a y-score? If you have no other information, the mean of the y-scores. Right? That's your best predictor. If x is not helping you in any way, because again, remember what we're trying to do. We're trying to predict the y-scores, hopefully using x. But if there's no relationship between x and y, my best predictor is just the mean of the y-scores. Knowing x tells me nothing. It doesn't help. Okay? So if r equals 0, right, so what does that mean? That means that the z of the y-scores equals 0. Well, what is 0 in z-scores? It's the mean of that distribution, right? It's the mean of that distribution. Okay? As r becomes smaller, there's less of a tendency to expect an extreme score on one variable to be associated with an extreme score on the other variable, right? If the correlation is weaker, then the strength of each score is not going to be necessarily the same. As long as your correlation is not 0, is not 0, you could take the first variable into account for prediction of the second. And this is something that comes up is how strong a correlation you have will determine how good a predictor you have, right? Which makes sense. How much of a relationship you have tells me how good a predictor you have. Okay? Now, there's a little concept. You may have heard these words, this phrase, regression toward the mean. You ever hear that phrase, regression toward the mean? I don't know how to change this. There, that's better, okay? Regression toward the mean, right? This was developed by a man named Sir Francis Galton, who was looking at the relationship. I've never heard this before. This is fun. Do you hear it? Y'all hearing that up there? Really? There's no rest. Okay. Yeah, it's bizarre. It sounds like music going on in the background. It's like feedback with harmonics or something. It's bizarre. Anyway, so Sir Francis Galton was interested in looking at the heights of parents and children. Okay? And what he noticed was that very tall parents tended to have tall children, but they weren't quite as tall as the parents. Whereas parents who were very short tended to have kids who were short, but a little taller than they were. What was happening was the heights of the children and parents were regressing towards the mean, regressing towards the middle. Why? Because the correlation wasn't perfect. Right? It wasn't a perfect correlation. So that's just the consequences of having an imperfect correlation. So he referred to it as regression towards mediocrity, but that's because he was like studying eugenics and things like that, so we're not going to get into that little history. But yeah, we refer to it as regression towards the mean. Again, because as your correlation decreases, your prediction gets closer to the mean if it's not perfect. Okay. Let's see if that, we have the lights down, a little mood music. Okay. One last thing I want to point out from this little slide is regression. We're talking about linear regression, just like I talked about in correlation, that the underlying data structure has to be linear for this to apply, that a straight line through it makes the most sense. If it doesn't, your results are going to be wrong. Again, you can throw all the stuff in SPSS, you'll get results. They won't be accurate, they won't be right. Okay? Unless your underlying data structure is linear, straight line. Okay. Now, I'm going to show you a variety of little different graphs here. Let's look at the bottom here, this graph on the bottom. This is just a graph if I transformed all my scores into Z-scores. The example that we're going to be doing a bunch of is using exam 1 scores to predict exam 2 scores. Okay, this is made up data. So my x variable is exam 1 scores, and my y variable is exam 2 scores. Now what I've done for this bottom graph is I've transformed everything into Z-scores, and I've graphed it. Okay? If you had a perfect correlation and you graphed this in Z-scores, the line would be a perfect 45-degree angle through the origin. Okay? The other thing that I want to show you that's interesting about graphing it in Z-scores is this. First of all, let's talk about the components of a line. All right? You know from, I don't know when they teach it anymore, 6th grade, 5th grade, 7th grade, the equation of a line. What's the equation of a line? Y equals mx plus b, right? Okay, you're right. Forget the notation. In statistics, or at least in the branch that we're looking at, the equation of a line is y equals bx plus a. I don't know why. This is just how it goes. Bx plus a. So what does b stand for? The slope. The slope. What is the slope? What is the slope? What does it tell me? Yeah.
How the two variables change in relation to each other?
Yeah. Some people will look at me and they'll all say rise over run, right? What the slope is for every 1 unit change of x, it's how much y changes. That's useful to know. For every 1 unit change of x, how much does y change? Okay? And in our equation, y equals bx plus a, so what's a? The intercept. The intercept. What's an intercept? The y-intercept. What's the y-intercept? Yeah, it's the value of y when x equals 0. It's where the line crosses the y-axis. Yeah?
In SPSS, would it be labeled as A, or was it?
No, in SPSS, it's not labeled as any of those things. I don't know why. They didn't ask me. Yeah, I think they refer to it as coefficients, regression coefficients. Okay? No, because that would make your life too easy. I think they have columns called coefficients and then standardized coefficients. There might be a beta in there. But they definitely don't have the word slope anywhere. And I'm reasonably sure they don't have B. And they usually have a box, and one line says constant, that's the intercept, and the other line underneath it, which name I can't remember, that's the slope. But you'll look at it in lab. But okay, so we have the slope and the intercept. All right? And those are like knobs that we tweak to get the best fitting line through our data. Right? The formulas that we have help us get this best fitting line. And we'll talk about what that means, what best fitting means in a minute. But let's go back to this graph for a minute, okay? If you have transformed all your scores into z-scores, and you calculated the equation of the line, the slope, b, is equal to r. The slope and the correlation coefficient equal each other if you've put all your scores into z-scores. That's the if. That's the caveat. And we'll see why that is in a moment. But your correlation coefficient equals your slope if everything's in z-scores. All right, let's take a look at some formulas. These formulas, by the way, they use population parameters. We're going to do them with sample statistics later, but essentially nothing changes majorly here. And you can even ignore this. This is how we get down to this, but it's not a big deal. It's in your book. This is the equation of the line. Y prime, your predicted y, equals bx plus a. Okay? Notice the subscript here is sub yx. That means you are regressing y on x. You're regressing. That's the phrase they use, regressing y on x. It means that you're predicting y from x. And if you were doing it the other way around, those would be reversed. I'm not going to do any examples where that's reversed. So sometimes I even drop the notation, but you should know that's what it is. Our slope, right, that's our slope, is equal to the ratio of these standard deviations times my correlation coefficient. Okay? Now, if I transformed all of my scores into z-scores, what's the standard deviation of a z-score? 1, right? So that would mean that that standard deviation is 1 and that standard deviation is 1. So what does that mean then? My slope is equal to my correlation coefficient, right? When everything is in z-scores. That's what I said before. Okay? So let us do some really, really simple examples, and we'll work up to somewhat more complicated examples, but nothing major league. first example we're going to look at in this first example, let's assume my correlation is equal to 1. Very rare, but let's just take a look at it. If that's the case, then the ratio of my standard deviations will give me my slope. Let me give you some data to work with. Y is height. Oh, I'm sorry, is weight, rather. Is weight. So the mean of weight is 155 pounds with a standard deviation of 15 pounds. And height is x. So I'm using height to predict weight. With a standard deviation of 69 inches and 3 inches. So if my correlation is perfect, then my slope is simply 5. 5, what does that mean? 5 what? What does that mean, that slope? Bring it back to this example. Yeah?
5 pounds per inch.
Yeah. For every inch increase in height, there's an increase of 5 pounds predicted. All right? So understand that even though your correlation is perfect, it's not that for every 1 inch change in height, there's a 1 pound change in weight. There would be, if you were doing it in Z-scores, you would expect a 1 standard deviation change in height to be associated with a 1 standard deviation change in weight, but not in the raw scores, not in the raw scores. Okay? Now, this is not simply our equation because we need the intercept. So let's actually do that. So I have to find my intercept, which is the mean of y minus the slope times the mean of x. So that's my intercept. Okay? Which means that my equation, the equation of my line, is again bx plus a, but in this case, my intercept is negative, so it's 5x minus the 190. The only thing, it's funny, everybody can do these computations. The only thing I see people make mistakes with are the negative signs. They mix that up because, you know, with the intercept, it's negative. With the equation of the line, it's positive. But what if your intercept is negative? Just be careful with it, okay? It's not a big deal. Just be a little careful with it. So that would be my equation of my line. So let's say somebody is 5'4", walks in, and I want to predict what their weight is going to be. How do I do it? How do I do it? Yeah. Exactly, right? I would just convert it to inches first, right? How many inches is that, by the way? Yeah, 64. And then plug it into my equation. So you'd predict their weight to be 130 pounds. Okay? Now, what if the correlation is not perfect? It's not 1. What if, let's say, our correlation is 0.7? What changes? If I change the correlation from 1 to 0.7, what changes in this? The slope changes. What else? All of it, right? Because if the slope changes, the intercept changes, which changes the equation. So let's actually just get this down. Again, it's the standard deviation of y divided by the standard deviation of x times your correlation coefficient. All right? Our intercept changes to this. So that the equation of my line equals this. Okay? Because again, remember, if you change your correlation, that means that that whole scatter plot is changed. So then the line is going to be different. Okay? Questions on any of this? I always think this is pretty straightforward. There's no big surprises here. Would anybody have questions about where something's coming from? We're good? Okay, good. So now we get, so the equation of the line is no big deal. What's a more interesting thing is how we quantify errors around a regression line. Okay? And again, right, so you have your data, you have your scatter plot, you put a line through it. If your correlation is not perfect, all the points don't fall on the line, which means there's some error. Your prediction predicts some things, but it's not perfect. There's error, there's uncertainty. How do we quantify that? How do we quantify that? Well, graphically, let's take a look at this upper graph for a minute. Okay, again, this is exam 1, this is exam 2. And you see the points are not on the line. All right? Don't look at this bit yet. We will get to it, but don't look at it yet. Just look at these. Graphically, what your error is how far is this point from the prediction? And how far is this point from what you would predict it to be? Or this point, or any of those points. Right? Graphically, how far the points are off the prediction line, that's your error. Okay. So what if I just found out how far each of my points was from the prediction, and I averaged them? What's the problem with doing that? Yeah? It's not the same line. It's not the same line, but I think you're intuitively getting somewhere, yeah? Yes, the average is 0. Does this sound like anything else we've learned from, the beginning of the semester? Deviation scores, right? Deviation scores from a mean. When we took all the deviation scores from the mean, we couldn't just add them up because they add up to 0. Why? Because the mean is like the fulcrum of a seesaw. It balances out those distances. Well, guess what? A regression line does the same thing. Regression line does the same thing. But the distance from the point to the prediction is not called a deviation score. It's called a residual. A residual. So here we have, right, a residual. A residual is the difference between the actual y value and your predicted y value. That's called a residual. But it's like a deviation score. So I can't just take the average of my residuals to quantify this error. What am I going to do with it? Square them, right? I'm going to wind up squaring my residuals. And when I square my residuals, that'll give me a sum of squares. And then, how do I find a variance? How do I find a variance from a sum of squares? Divide by n, or degrees of freedom. Okay? We're still dealing with population parameters right now, so it's going to be n. But that's the same idea. Same idea. I told you at the beginning of the semester, a lot of the themes stay the same. The details kind of change. But this is the same idea. So a residual, it's the amount of the original value that's left over after the prediction is subtracted out. So let's see how we're going to use it. We're going to use it in something called the variance, right? It's a variance of the estimate. So it's like a variance, but it's called of the estimate because it's for a regression formula, regression line. All right? And the variance of the estimate is the variance. How far, right? What's a variance? What does a variance tell me? A regular, good old-fashioned variance. What does a variance tell me? What do I use a variance for? If I asked you standard deviation, it's the same idea. What does a variance tell me? Yeah?
On average, how much the scores differ
From
each other or
from the mean, right? It's a kind of average amount of how far scores differ from the mean. Well, the variance of the estimate is about how far scores differ from the regression line. So let's take a look at the formula. It should look just like a sum of squares to you. How far my score is from my predicted score, squared, added up, divided by n. That's it. And notice the notation, variance with the estimated y, the variance of the estimate. This is also called residual variance, which makes sense if those are called residuals, so we call it residual variance. You might hear that term. Okay? As your correlation gets bigger, what happens to the points? Do they get closer to the line or further from the line? As your correlation gets bigger, they get closer. As your correlation gets bigger, the variance of the estimate gets smaller. There's less error. Right? Think about it. If your correlation is 1, that's perfect. It's a perfect predictor. There's no error. But as the correlation starts getting weaker and weaker, there's more error. So the variance of the estimate is going to be larger. Okay? Now, there's another little point here. When the correlation equals 0, the variance of the estimate is the largest, and the regression line becomes horizontal. I talked about that before. Let's take a look at it again. Because it kind of gets back to this idea of quantifying the errors and what they really mean. Okay, so let's assume the correlation here is 0. The best line through there is just a horizontal line. It's not helping us. The line is at the mean. Okay? The variance of the so that means that my best predictor here is what? In this case scenario, what's my best predictor? The mean, right? That's all I've got. Okay? Which means that my residuals are really going to be, right? The residual is my actual score minus my predicted score. What's my predicted score going to be here? The mean. If I squared those, added them up, and divided by n, guess what that is? Does anybody know? Does anybody recognize that formula at all? It's just the variance of the y-scores. It's the variance of the y-scores. Right? That variance of the y-scores is also usually referred to as the total variance. The total variance. Okay? So what that's saying is if your correlation is 0, the variance of the estimate, that's this, is the same as that. It's not helping you at all. That other variable is not helping you, right? You want this to be small. But if your correlation is 0, that is, there's no relationship between these two variables, then the variance of the estimate is going to be the same as the variance of the y-scores. It doesn't help you. It doesn't help you. As your correlation gets bigger, this gets smaller. The variance of the estimate gets smaller. And then that helps. And then that helps. Then it'll be smaller than the variance of the y-scores. Okay? Questions on that? This is what you want to do essentially, all right? When you have these two variables, you're looking at x because you want to predict y. But one of the things you're interested in is why does your y variable, why does everybody have different scores? Like if we're looking at exam 1 and exam 2, you know, the scores are different. Look especially at exam 2. Everybody has a different score. The question is, why does everybody have a different score? Can I use their performance on exam 1 to predict how they're going to do on exam 2? So I'm talking about how much the differences in the y-scores can be accounted for by how they do in exam 1. So I'm always interested in seeing how I can understand the variance of the y-scores, that. All right? So this is the amount of error associated with that prediction. Okay? So that's all I've just said. For any correlation that's larger than 0, then it'll be smaller than the variance, and that shows you the advantages of the regression that you're doing. Okay, fine. So now we have to talk about this variance, because what we're going to do is we're going to take these residuals. We have the variance of the estimate, but we're going to talk about more measures of variance here. So let's actually take a look at the graph first. And again, all we're doing now is quantifying error. Quantifying error so that we can determine how much our regression line helps us in prediction. Okay? We're going to take 1 point and look at it. But this 1 point will represent, like, you really have to think of it as doing it for all the points. Okay? As a matter of fact, you know what I want to show you first? Just as a comment on the residuals. I just want to go back to residuals for a moment, just so you understand kind of in numbers, because I know sometimes that's easier. Let's imagine, here's the equation of the line, by the way. Exam 2 is equal to 1.119 times exam 1 minus 41.8. Okay? That's the equation of that line, going through that data. All right? I calculated it, or I got it through whatever program it was I used. I think it was a program called Fathom, actually, to do that. That's the equation of that line. You could look at it like this. You could rewrite it like this. Bless you. Okay? Usually if you put the names in the computer programs, they'll spit it out, the equation that way. Okay? So let's imagine that I have an x value, an exam 1 score of 89. Okay? So then I want to know what my predicted y is going to be. That's what I would predict my y to be. But if I look at the data for a score of x equals 89, my real y value is 57, right? Because I have the data. This prediction line that we calculate is really for any new scores coming in. Okay? So then what would my residual be? That would be my residual. So understand something. If you were going to calculate the variance of the estimate this way, can you understand how annoying this would be? Like, do you see all the steps involved? You'd have to have a column of your y-scores. You'd have to find the equation of your line and find a column of the predicted scores. And then you'd have to subtract all of them, right? And then you'd have to square them and add them up, and then divide by n. That would be the variance of the estimate. We're going to have an easier way of doing this, but I just wanted to show you this is where this is coming from. Anybody have any questions on where any of these numbers came from? Okay. Okay, good. So, to get back to our variance that's explained and unexplained, we're going to take 1 point. You see this point? That's an actual data point. So, like I said, you have to imagine this applies to all the points, but we're only going to look at one because it'll make the graph too messy. Okay? This point differs from the mean. This is the mean. Okay? So we can look at this as the difference between that point and the mean. Right? If I did that for all the points, the difference between the actual data and the mean, if I did it for all the points, squared, added them up, divided by n, That would give me the total variance. The total variance. Okay? Each of these little things is broken up into two components. All right? This difference here is broken up into two components. Here is the difference between, right, from this point to that point. That's the difference between my score and my prediction. What is that? The residual. Okay? If I did that for all the points, squared, added them up, divided by n, that would give me the variance of the estimate. The other thing that we call that is unexplained variance. Unexplained. Unexplained. We don't know why exactly that point isn't on the prediction line. We don't know. Individual differences. There's all sorts of explanations. But it's unexplained variability or unexplained variance. Okay? So that's the first component. The second component is the difference between my prediction and the mean. The difference between my prediction and the mean. Yeah?
Can you just give an example of what, like just an example of a residual? Is it kind of like, so it's something, or something that's unexpected versus expected in an actual?
Yeah, well, let me explain this, and let's see if that helps, okay? If it doesn't, bring the question back, okay? So this component is the difference between my prediction and the mean. If I took all of those, squared them, added up, divided by n, that would give me another variance. That variance is called the explained variance. The explained variance. So you see, the explained variance and the unexplained variance add up to the total variance. Now, when we say the explained variance, what we mean is how much better at prediction the regression line is than using the mean. That's really what that is. Explained variance is how much better the regression line is at prediction than the mean. Okay, so to kind of get back to your question, if I want to predict this, if I want to predict a y-score, what are my options? Well, my option is to use a mean, the mean of the y-scores, or a prediction that I can get from the regression line. Okay? If I use from the regression line, there's going to be some slop because it's not perfect. Again, because the correlation is not perfect. The correlation between exam 1 and exam 2, it's not perfect. It tells us something, but it doesn't tell us everything, right? Because how you did on exam 1, right? Well, maybe you didn't do quite as well that day because you had a fever, or you were preoccupied with something else, or you had 5 other midterms that day, you know? So that all goes into that. That's your unexplained variance, whereas the explained is the other possible predictor, right? Either the mean or your prediction, right? Y prime. And the difference between the prediction and the mean is how much better your regression equation is at predicting it than the mean is. Right? If your correlation is a good amount, then it's a much better predictor. Okay? So again, so that's what's going on. Let's take a look back at this one. Right? So this is what we have here. This is if you just took 1 point. And you could do it with the numbers. You could just take 1 point and see that your unexplained and your explained add up to your total. But if you did this for all of these terms, they're just variances. They're just variances. Again, you're looking for a correlation that's not 0 to make that variance of the estimate smaller, the unexplained variance smaller, and the explained variance bigger. Because if the explained variance is bigger, then it's a better predictor than the mean. Okay? Questions on any of that? Yeah, go ahead.
You mentioned that the unexplained variance and the explained variance added together is the total variance.
Yeah.
But in the equation you just had, the sum of y minus y bar squared over 2, that's, you could just call that total variance.
Over what? Did I have 2?
Or over, sorry, over n.
Is what? Which? Tell me again.
Just that, yeah, that part.
Yeah.
So that equals total variance?
This is the total variance.
Okay.
Yeah. Again, what is this? This total variance is what? It's just the variance of the y-scores. It's just the variance of the y-scores. You might see the terms used interchangeably. It's a good idea for you to remember that that's what it is. Okay?
But it has nothing to do with the predicted y.
That's right. It doesn't have to. Right? Again, this is what you have. You have a bunch of y-scores. They're all different. There's variability. What's the variability? The variance of the y-scores. How much of that is due or can be explained by how people do on exam 1 and how much can't? Okay? They're different measures. They're all variances, but they're different measures of things. Okay? And actually, yeah.
So when unexplained is less than explained variance, is it matter of predictor, then it's the other way around?
Yeah, sure. Sure. Yeah. Okay. So the problem, what's the problem with a variance? If I told you that the variance of something is 25, what's the problem with that? 25 what? We don't know what that means, right? Variance, especially variance, sum of squares, they're measures of variability, but they're not like the standard deviation, which is in the original units. So it's a little hard to understand what that means. So what do? We take these variances and we turn them into proportions of the total. And then we have a better understanding of what this means. What is this called? The first one we're going to look at is something called the coefficient of determination, which always makes me think it sounds like something from Lord of the Rings. The coefficient of determination. But essentially, so let's look at this for a minute, okay? The coefficient of determination is, this is the formula, it's my explained variance out of my total variance. It's a proportion of my total variance. We're just taking the explained and turning it into a proportion of the total. Okay? So look, it represents the proportion of the total variance that is explained by the predictor variable. Now, how would I normally get this? Well, what was my explained variance? How do I get my explained variance? What minus what? What is the explained? Look back at it. Look back at the formula. What's explained? Yeah.
How much better the prediction is than the mean?
Yeah, but like literally, what was it? Y minus y what minus y what? What was it?
Y prime minus
Yeah, y prime minus y bar, okay? So think about what you'd have to do for that. You'd have to find all the predicted values, subtract those from the mean, right, and get your column, square those, add those up, and divide by n if you wanted that variance, okay? Here's a much easier way to do it. The coefficient of determination is simply r squared. R, our correlation coefficient, r. Square that, and you get the coefficient of determination. That's it. So, for example, in the exam 1, exam 2 scenario that we have, the correlation between the two variables is 0.91, which is crazy big, right? R squared, then, is 0.83. R squared is 0.83. So what does this mean if we were going to say it in words? Listen first, I'll repeat it again, okay? It means 83% of the variability in the exam 2 scores can be explained by performance in exam 1. Okay? I'll repeat it. Let's see. 83% of the variability in exam 2 scores can be explained by performance in exam 1. Okay? So step back from it. You all wrote it down. Step back and see if it makes sense what you just wrote down. Right? What you're saying is a big chunk of the differences in those scores can be explained by how they did in the first exam. Okay? Now, let me just let you know, I use the word explained by. Very often you will hear explained by, predicted by, or accounted for. Accounted for is a big term people use. 83% of the variability in exam 2 is accounted for by performance in exam 1. Hang on just a second. So accounted for is the kind of term you'll see a lot. I kind of like explained by because it makes a little more intuitive sense to me, but you're going to see accounted for a lot. Yeah?
Would this be the type of thing that you could explain the height experiment with? Like, blah, blah, blah percent of children's height can be explained by their parents, or is that
Yeah. Exactly. Exactly. If you're looking at correlations between any two things, then you could calculate an R squared and talk about it. Again, it's not saying causality, right? It's not saying that the height of the parents causes the height of the children, but just if you know the parents' height, it can help explain what's going on in the children's height, or it can predict, which is not the same thing as control or cause. Okay? Yeah?
Can you just explain, like, the difference between R and R squared? Like, why is it, I thought correlation
Correlation gives me a measure of the strength of the relationship. That is, how much do extreme scores on one variable tend to have extreme scores on the other variable? Right? That's one way of thinking about it. Whereas this is actually giving me a percentage of how you can think about the variability in one variable. It's all related, but it's not, it's not exactly the same thing. Yeah? Okay. Okay? So this is a very powerful term, and this is the kind of thing you might see in a lot of journal articles. So it's a good idea to get on top of this. I'm not going to give you guidelines on for what's a lot of variability and what's not, because it's really hard to tell, and it's really hard to tell in any particular discipline. Also, we're just doing simple linear regression. We just have two variables. If you're going to do something like multiple regression, which is chapter 17, and we're not going to do it, that's looking at multiple factors to determine or predict another variable. All right? Then you would have lots of bits and pieces. Like if you want to predict crime, okay, in a particular neighborhood, you might look at a variety of different variables to predict that. And each one of them will have their own correlation with crime and their own regression weight. By the way, we call a slope a regression weight. You'll see that term. A regression coefficient or a regression weight. Okay? So all of those things will add up. So we have 83%. That's like a whopping big crazy number. Because again, what's the largest it can be? 1. The largest it can be is 1. By the way, if R squared is equal to 1, well, that means that R equals 1, right? What does that mean about my explained variance and my total variance? Think about the formula for a minute. If R squared is 1, what does that mean about my explained variance and my total variance? Yeah? They're the same. Meaning, my explained variance explains my total variance. All that variability I can explain with this other variable. Okay? Okay, so that's the coefficient of determination. What's the coefficient of non-determination? Well, that's the unexplained variance over the total. The unexplained over the total. What's another name for the unexplained variance? The variance of the estimate. The variance of the estimate, that's that. Okay? So it's the variance of the estimate over the total variance. Now this 1 minus r squared, right, because it'll all add up to 1, this is generally noted k squared. So k squared is the coefficient of non-determination. Because this relationship with the variance of the estimate, this gives us an easier way to figure out the variance of the estimate. Here's the formula. Okay? We just solve for 1 minus r squared instead. So here's an easier way of finding the variance of the estimate than the definitional formula I showed you before. Much simpler. Here, you need to know the variance of the y-scores, and you need to know the correlation coefficient. That's typical. You would likely know that stuff. So what do you want? You want the coefficient of determination to be as high as possible, and the coefficient of non-determination to be as small as possible, ideally. Okay? I think we're up to an example. Does anybody have questions on this? So this example, by the way, here's the scatter plot for it, is this top thing. This is an example where we're looking at children first through 6th grade, and we're looking at their age versus their test scores on a verbal comprehension test. Here's the scatter plot. From the scatter plot, what do we think about this correlation? What does it look like? It's positive, right? As age is increasing, their verbal comprehension scores are increasing. And it looks like a pretty strong correlation. Okay, so I have the equation there, but let's calculate it. Now, if we're doing sample statistics, this is what we have. Okay, I've just substituted with the sample statistics, but the structures of the formulas are the same. And down here, we have the means for age and score. We have the standard deviations, the correlation coefficient, and n. What does n stand for? Well, try not to think of it, you're right, but try not to think of it as the number of kids in the study. Think of it as the number of pairs of scores. The number of pairs of scores. Because you might be correlating two things that are not the same kids, right? Like if you're correlating, let's say, like we've been talking about height and weight, it's in the same person. But what if you're correlating crime in a neighborhood and poverty levels? Okay? That's not strictly the number of people you're counting then. Number of pairs of scores, I would say. Pairs of scores is probably a better way to think of it. Okay, so how do we do this? Very simply. Let's get our slope first. And the correlation here is 0.72, so that's large and positive. What does 0.249 mean? In this example, what does it mean? What is it standing for? 0.249 what? Sure. .249 what? Yeah.
0.249 points, I guess, on the test over for every month.
Yeah, right? For every 1 month increase in age, we expect their score to change by 0.249 points. Okay? Now let's get our intercept. That's my intercept. Making the equation of the line that's the equation of my line. Right? Pretty simple. Which thing? See, if I put it all the way down there, I have about 1 inch left to write on. So I have to keep shifting it up and down. Okay? So now, if somebody came to you and said, hey, I have a 10-year-old, what do you predict their exam score to be? What do you do? Good. First convert it into months, then?
Yeah, you put it as X.
Yeah, just plug it in. Just plug it in. I'm going to have to write this up here. For a 10-year-old, so what are the months? Yeah. Just be careful of your units. Like, pay attention, you know? All right, now, the other thing, I want you to notice here is, does that value, 35.8, does that make sense given your data? Again, this is just an estimate, but I want you, when you're doing these computations, to see whether things make sense. It keeps you from a lot of grief in your computations. Does that value make sense, and if so, why? Again, you're not going to get an absolute value here. It's just kind of in general, does that value make sense? Why?
Because, well, like, according to this graph,
Yeah.
because both 120 and 35 are on the higher range of the...
Okay, they're on the higher range. Were you going to add something to that? No? Were you going to add something to that? Does anyone want to add something a little more specific to that? Yeah.
That point was close to the regression line.
No, it's not even just that. They're in the higher end, but I want to be even a little more specific. They're both higher than the mean. They're both higher than the mean. Okay? So now, if I wanted to find the coefficient of determination, that's simply this, right? So what do I say here? What does this mean? Anyone want to take a stab at what that means? Yeah.
52% of the variability in exam scores can be explained by age and months.
Yeah, right? 52% of the variability in the test scores can be explained by or predicted by their age, which makes sense. Okay. Now, my coefficient of non-determination . 48% of the variability can't be explained. Okay. So now what I'd like to do is I'd like to calculate homogeneity of variance. I'm thinking of something else. The variance of the estimate. Here's the variance of the estimate if you're using sample statistics. Before was population parameters. Here's with sample statistics. Notice, what's the major thing that changes? Well, yeah, that's S. It's not sigma. What's the major thing that changes? We're dividing by what? Degrees of freedom. Big N minus 2, not N. That's the definitional formula. This is the computational formula, the easier one. So let's actually do that for this example. What's N here? It's on your data.
100.
Yeah, 100. And I didn't give you the variance of the y-scores. I gave you the standard deviations. You have to remember to square it here. Okay, so that would be the variance of the estimate for this example. And again, it's a measure of how far scores are scattered. But what if I wanted to make it in the original units? What would I have to do? Just take the square root, right? Just like we did with standard deviation. If you have a variance and you want to get back to the original scale, you take the square root of it. That gives you this bottom thing, the standard error of the estimate. It's just the square root of the variance of the estimate. So look, this one is for the population. This one is for the sample. So in this example, it's simply the square root of this, which equals whatever that equals. And it's 5.06 what? 5.06 items correct. Because again, it brings it, or points on the score, it brings it back to the original units. Okay? Everybody reasonably good with that? Yeah. Yeah, or points, or points, what?
5.06 items correct is one standard deviation away from.
No. It's one standard error of the estimate away from the regression line.
Okay, so that's how far off your estimate was, in other words?
Yeah, it's kind of a measure of how far the scores are off from your predictions. Yeah. Yeah. Okay? Anything else? Because I think this is a good point to stop at. All right? So I will see y'all next week.